Alright guys and girls, this is my second video on using the reference tables. Just a quick review of how each of the reference table sections for the various rock types, how it works. So in this one we're looking at the scheme for the igneous rock identification. And it's going to be broken into three separate sections. On the bottom is the mineral composition. These are all minerals that you had seen during the mineral identification lab. Specifically, the ones that we pay close attention to would be on the left side, the potassium and quartz, and on the very right-hand side, the olivine and pyroxene. The others that come through the middle, you'll notice that they cross from left all the way to right-hand side to some degree or other, and they're not unique for that reason. They kind of exist in all different worlds. So we tend to sort of not pay much attention to those. But the ones on the left have specifically these three characteristics. They have a light color, they have a low density, and they're what we call felsic because they're rich in aluminum and silicon. If you check your page 16 reference tables, mineral compositions, you'll see that silicon and aluminum are very present in those two. So further up from that are igneous rocks that form from these minerals. So if we look at this divider line that comes right down the middle right here, anything that's directly above these two minerals are going to be felsic rocks. So pegmatite, granite, rhyolite, vesicular rhyolite, and even pumice and obsidian are felsic igneous rocks. Now on the right-hand side, pyroxene and olivine, we can do the same kind of thing. Here's this divider line that comes down, and everything on the right side, the whole right half, and I know there's other dotted lines here, just ignore them. Everything on the right side of this line in the middle here, everything up there is going to be a rock that tends to be very dark in color. They're high density, and they contain magnesium and iron in them. So we have gabbro, diabase, basalt, vesicular basalt, scoria, and basalt glass, and also peridotite and dunite. These are very rare rocks that are from the mantle, so there's not a whole lot of these things available, so that's why they're such small boxes. Now, the next thing we want to look at, let me clean up this chart just a little bit, but the next thing we want to look at is along the top half of the chart, and we're going to zoom in on the environment of formation. So we have intrusive rocks that are sometimes called plutonic, and we have extrusive rocks that are sometimes called volcanic. And if we draw a line right down the middle, then it separates into those two different kinds. So granite, pegmatite, diorite, gabbro, and these other two, they are coarse or maybe very coarse grain rocks. I just lump them together and call it coarse. They're all greater than 1 millimeter in size. This means they cooled deep underground very, very slowly. And the minerals had a long time to grow, and they got to be very big. 1 millimeter and larger is considered big. And then on the top half, exactly the opposite of that. We have fine-grained rocks. These are rocks that form in a volcanic process, and they didn't have a whole lot of time to cool, so they have very small crystals, rhyolite, andesite, basalt. You can see some crystals, but they're really super tiny. And then above that are the glassy crystal, the glassy texture, and glass means that there are no crystals at all. It's almost like an instant freezing of the lava. So pumice, obsidian, basalt, scoria, these all have no crystals whatsoever. And you also see this word vesicular that appears here. Vesicular means it has air bubbles in it. You remember in class I showed you some examples of rocks that have air bubbles in them.